Prepare for a spine-tingling dive into the mysterious workings of our planet as we grapple with a stark reality. The poles are shifting and our protective magnetic field is faltering. An ominous spectacle unfurls, heralded by the acclaimed physicist Michio Kaku. With continents inching around like colossal jigsaw pieces and magnetic poles racing across the globe, our Earth is in the throes of monumental changes. As our magnetic shield wanes, we stand on the precipice of the unknown, staring into the abyss of cataclysmic outcomes. This is no dystopian fantasy, but a scientifically grounded alarm. We need to brace for the unexpected. Rewind about 300 million years and our world looked very different. An enormous landmass known as Pangaea was all there was, but as the Earth spun on its axis and the eons rolled by, this supercontinent began to fracture, tearing apart to form the continents that we know today. But how exactly did this monumental shift occur? The credit goes to plate tectonics, the scientific theory that describes how Earth's lithosphere, its uppermost layer, is divided into a patchwork of rigid plates. These plates, some bearing continents, others vast expanses of ocean, float atop the partially molten, more flexible layer of the asthenosphere. As the asthenosphere circulates in convection currents driven by Earth's internal heat, it nudges the plates above, propelling them in various directions. The result, the gradual but relentless shift of continents across the Earth's surface. Now imagine Pangaea, this colossal supercontinent encompassing all landmasses. As tectonic forces go to work, cracks appear in its fabric, cleaving it apart. Over the course of millions of years, Pangaea ruptures and fragments into drifting continents, each charting its own unique course. This evolutionary journey has sculpted the world map we recognize today, with North America, South America, Africa, and Europe as distinct entities. But this relentless continental shift isn't merely a curiosity of Earth's history, it's a process still in motion today, molding our planet's future. As you read this, the Atlantic Ocean widens by a few centimeters each year, pushing the Americas away from Europe and Africa. In contrast, the Pacific Ocean shrinks as its floor is forced beneath the edges of the American and Asian plates, leading to the formation of deep-sea trenches and volcanic activity. These ongoing continental gymnastics, however, are but the tip of the iceberg. Beneath this surface drama, a more profound shift is underway that could usher in unparalleled global changes, a pole shift. As we stand on the brink of these monumental shifts, understanding the mechanics and consequences of such transformations is no longer an academic exercise. It is a matter of global interest and survival. So brace yourself as we journey into this uncharted territory, guided by the insights of eminent scientists like Michio Kaku. Science, in its relentless pursuit of truth, often encounters phenomena that at first glance seem inexplicable. Yet these mysteries serve as gateways to deeper understanding, challenging our perspectives and stretching the limits of human knowledge. And amidst these mysteries, we find intriguing hints at possible connections to the planet's ongoing pole shifts. And three such phenomena merit our focus: erratic animal behavior, sudden climate changes, and the Bermuda Triangle enigma. Animals, particularly migratory species, exhibit a profound sensitivity to Earth's magnetic field. They utilize this invisible force to navigate across vast distances with uncanny precision. However, in recent times, numerous instances of animals veering off their traditional routes and behaving erratically have been reported. For example, the massive bird die-offs and stranding of whales at unusual locations might not be random tragedies, but ominous signs of a magnetic field in flux. If these poles are indeed shifting, we would expect these magnetic misalignments to increase, a hypothesis backed by increasing reports of such incidents. And then there is climate change, which is no longer a disputed topic, but the pace and severity of its effects often baffle scientists. Some theorists propose a connection between Earth's magnetic pole shifts and climate change, postulating that a weakened magnetic field might exacerbate the effects of solar radiation on our planet's climate. While this remains a subject of intense research, the correlation between the dates of previous pole reversals and abrupt shifts in Earth's climatic history suggests a potential link. The exploration of this connection could be crucial in predicting future climate patterns and preparing for the implications of a changing environment. And thirdly, we have the Bermuda Triangle. Notorious for its unexplained disappearances of ships and aircraft, it has long piqued the curiosity of scientists and laypeople alike. Some researchers have proposed a magnetic anomaly within the Bermuda Triangle as a possible cause of these disappearances. Could the high incidence of navigational errors in this region be tied to the effects of an active pole shift? Studies have noted that the Bermuda Triangle is one of the few places on Earth where true north and magnetic north align, causing compass deviations. If Earth's magnetic field is indeed changing, such anomalies might become more widespread, leading to increased navigational challenges. In decoding these mysteries, we are reminded that the world we inhabit is a dynamic and complex system, vulnerable to forces that we are only beginning to comprehend. Pole shifts, once considered a geological curiosity, now emerge as a significant agent of global change, potentially influencing the very way we live and perceive our world. And unraveling these connections requires a multidisciplinary approach, uniting geologists, climatologists, biologists, and physicists in a common quest. And as we venture deeper into this labyrinth of scientific puzzles, we are guided by luminaries like Michio Kaku. The journey is fraught with uncertainties and profound implications, but, as history has proven, it's in grappling with such mysteries that humanity's ingenuity and resilience truly shine. As the poles shift beneath us, we stand at the dawn of a new era of scientific exploration, heralding discoveries that could redefine our understanding of the Earth and ourselves. So first, what is a pole shift? In the context of planet Earth, a pole shift refers to a drastic change in the geographical or magnetic pole's positions, or both. In this section, we will delve into an in-depth examination of both types of pole shifts, geographical and magnetic, delineating the causes, occurrences, and impacts. Geographical pole shifts refer to the physical movement of the Earth's poles, altering the tilt of the Earth's axis. A chief driver of these shifts is known as true polar wander, a phenomenon that occurs when an uneven distribution of mass within the Earth causes the planet to tilt and reorient itself. Factors contributing to this mass imbalance can include changes in the Earth's mantle, accumulation of ice at the poles, or significant seismic activities such as volcanic eruptions or earthquakes. Although these geographical pole shifts can be quite dramatic, they occur over geological timescales, millions of years, and are therefore not immediately perceivable by humans. On the other hand, magnetic pole shifts, also known as geomagnetic reversals, are changes in the Earth's magnetic field in which the magnetic north and south poles switch places. Unlike geographical shifts, these magnetic reversals are less predictable, in fact, seemingly random, with intervals ranging from thousands to millions of years. Magnetic pole shifts are driven by dynamo effects in the Earth's core. The Earth's magnetic field is generated by molten iron within the outer core swirling around, creating electric currents which in turn produce a magnetic field. When the flow of molten iron changes, this can alter the magnetic field, causing the magnetic poles to flip. And it's worth noting that we are currently undergoing such a magnetic pole shift. Over the last 200 years, the magnetic North Pole has been moving at an average rate of 10 kilometers per year towards Russia. This shift does not happen overnight, but occurs gradually over hundreds to thousands of years. The implications of pole shifts, both geographical and magnetic, are profound. Geographical pole shifts can lead to significant climate change due to the alteration of the Earth's axial tilt. This could potentially affect sea levels, alter prevailing wind patterns, and shift climatic zones. Magnetic pole shifts, on the other hand, could have considerable effects on navigation systems, as many of these rely on Earth's magnetic field. This shift could also influence migratory animals that use the magnetic field for orientation. And from a technological perspective, a weaker magnetic field during a pole reversal could allow more solar radiation to reach the Earth, potentially damaging power grids and satellite communications. Magnetic pole shifts represent an intricate dance between Earth's crust and its molten core, shaped by forces deep within the planet. Understanding these shifts is not only a testament to human curiosity and scientific endeavor, but also crucial in foreseeing the potential challenges our planet may face in its continual evolution. As we delve further into this fascinating phenomenon, we unravel more about the Earth's past and potentially our future. In our quest to understand the fascinating yet complex phenomenon of pole shifts, numerous scientific luminaries have made significant contributions. In this section, we'll delve into the theories proposed by three such titans of scientific inquiry: Sir Isaac Newton, Albert Einstein, and Charles Hapgood. Newton, in his monumental work Philosophiae Naturalis Principia Mathematica, highlighted the role of gravitational forces in the movement of celestial bodies. Although Newton didn't explicitly discuss pole shifts, his laws of motion and universal gravitation provide a foundational understanding of how mass imbalances can trigger changes in the Earth's axis, a principle central to explaining geographical pole shifts. Einstein, famed for his theory of relativity, engaged with the topic of pole shifts through his correspondence with Professor Charles Hapgood. Intrigued by Hapgood's idea of crustal displacement, Einstein suggested in one of his letters that significant accumulation of ice at the poles could impact the distribution of the Earth's mass, causing the crust to slip over the mantle, effectively reorienting the geographical poles. While Einstein did not necessarily endorse Hapgood's theories, his thoughtful engagement indicates the scientific plausibility of such dramatic shifts. Nonetheless, it's worth noting that this theory remains controversial, with many geologists and geophysicists arguing that there's insufficient evidence to support such a comprehensive crust displacement. Hapgood, a history and science professor at the University of New Hampshire, is perhaps the most directly linked to the concept of pole shifts. In his book The Earth's Shifting Crust, 1958, he proposed the theory of Earth crust displacement. Hapgood suggested that the Earth's entire crust could shift in one piece over the more fluid layers below, leading to rapid relocation of the geographical poles. The phenomenon of pole shifts has been touched upon by some of the greatest minds in history, each contributing their unique perspective and theories. From Newton's foundational principles of motion and gravity, Einstein's engagements with crustal displacement theory, to Hapgood's bold assertions about the Earth's shifting crust, these luminaries' contributions continue to inspire contemporary investigations into this captivating geological enigma. Through these theories and evidence, we are able to further probe the mechanics of our dynamic planet and the continual process of its transformation. Now, the speed at which pole shifts occur has been a topic of much scientific debate. In this section, we focus on the views of Charles Hapgood, a key figure in the discussion of pole shifts and how his theories have evolved over time. Hapgood's initial theory of Earth crust displacement proposed that the entire crust of the Earth could move as a single unit over the fluid asthenosphere below. He suggested that this could result in a dramatic shift in the location of the geographical poles, potentially occurring over a short geological timescale. This, Hapgood argued, could explain various anomalies like the sudden extinction of large mammals during the last ice age and the unexplained accuracy of ancient maps such as the Piri-Reis map. However, the issue of pole shift speed proved controversial. Critics argued that the immense forces required for such a rapid and extensive displacement of the Earth's crust would be so destructive that they would essentially rupture the planet. This significant opposition led Hapgood to revise his theory. However, despite these adjustments, Hapgood's theory remains a subject of debate within the scientific community. The majority of geologists and geophysicists agree that while pole shifts have occurred throughout Earth's history, they most likely transpire on a much slower timescale than Hapgood originally proposed. The prevailing theory is that they are driven by processes such as plate tectonics and mantle convection over millions of years. However, Hapgood's changing views on the speed of pole shifts reflect the dynamic nature of scientific inquiry. Theories are continually revised and refined in the face of new evidence and criticism. While his theories have not gained widespread acceptance, they have nonetheless made a significant contribution to the ongoing debate about the nature and speed of pole shifts. The questions raised by Hapgood's work continue to inspire researchers to deepen our understanding of this complex and fascinating planetary phenomenon. And it's worth noting at this point that in the world of scientific mysteries and enigmas, the life and death of Charles Hapgood holds particular intrigue. Hapgood, a prolific history professor and researcher, ventured into the complex theories of Earth crust displacement and pole shifts, offering fresh yet controversial perspectives that defied conventional scientific understanding. His death in 1982, however, has since been the subject of various speculations, adding a layer of mystery to his legacy. Hapgood's death was reported as a result of a car accident, a pedestrian hit by an automobile in Greenfield, Massachusetts. For many, this appeared as a tragic, albeit straightforward incident. But as news of his demise spread, conspiracy theories began to circulate, painting a different picture of the event leading up to his death. These theories were fueled by the controversial nature of Hapgood's research. His ideas not only challenged accepted scientific norms, but also raised questions about the Earth's history and its potential future. And it was the uniqueness and radical nature of his propositions that opened the door for conjecture that his death may not have been accidental. It is important to note that these theories, while intriguing, are speculative in nature and lack substantiated proof. The official account of Hapgood's death remains that of an unfortunate accident. Still, these conspiracy theories surrounding his demise are testament to the profound impact Hapgood's work had on public imagination and the ongoing intrigue his theories continue to evoke. In the realm of science and exploration, Charles Hapgood remains an enigmatic figure, his life marked by intellectual audacity and his death shrouded in mystery. Regardless of the controversy surrounding his demise, Hapgood's contribution to the discourse on pole shifts and Earth's geological history endures, keeping his legacy alive in the annals of scientific exploration and debate. And within the realm of pole shift theories, there is another name, Chan Thomas, that reverberates with significant impact. An author and researcher, Thomas delved into the realm of cataclysmic pole shifts in a way few others had, articulating a theory that shook conventional scientific norms and provoked both interest and skepticism in equal measure. In his controversial book, The Adam and Eve Story, The History of Cataclysms, Thomas presented the idea that Earth has experienced multiple cataclysmic pole shifts in its history. These cataclysms, as he suggested, were not gradual millennium-spanning processes, but rather sudden, devastating events occurring approximately every 5,000 to 6,000 years, causing widespread destruction and dramatically reshaping the Earth's geography. Thomas posited that these cataclysms were triggered by an accumulation of ice at the poles, which eventually destabilized the Earth's crust, leading to a catastrophic displacement. This displacement would cause the Earth's crust to slide over the mantle, shifting the position of the poles and causing massive floods, volcanic activity, and seismic events. However, this concept differed markedly from the theory proposed by Charles Hapgood, who suggested a much slower, less violent displacement. In contrast, Thomas's theory presented a picture of sudden and catastrophic change, a global upheaval that would obliterate civilizations and drastically alter life on Earth. In the end, the enduring legacy of Chan Thomas may be his contribution to our understanding of the Earth as a dynamic, ever-changing entity. His bold ideas serve as a reminder that our planet's history is full of mysteries and that our understanding of it is continually evolving. While his cataclysmic pole shift theory remains contentious, his explorations into this complex topic continue to intrigue and inspire ongoing research and debate. Now, the heart of Chan Thomas's cataclysmic theory lies in his book, The Adam and Eve Story, The History of Cataclysms. Through this fascinating work, Thomas presents his vision of Earth's past, challenging the viewer's perspective on established geological and historical narratives. The Adam and Eve story suggests a cyclical nature to Earth's history, marked by regular intervals of dramatic, destructive change. Thomas theorizes that approximately every 5,000 to 6,000 years, the accumulated ice at the Earth's poles triggers a catastrophic shift, causing the Earth's crust to slide over the mantle. This sudden displacement, as per his theory, results in devastating floods, increased volcanic activity, and massive seismic events. He goes on to suggest that the human history as we understand it is but a blip in the face of these catastrophic cycles. Each cataclysm, according to Thomas, obliterates existing civilizations, erasing our collective memory and forcing humanity to start from scratch. He further connects these cataclysms with many of the ancient legends and myths about world-ending floods and catastrophes. Thomas sees these legends not as mere myth but as vestiges of historical truth distorted by time. He presents the biblical story of Adam and Eve as one such myth, arguing it's a symbolic representation of human survival and rebirth following a catastrophic event. In his interpretation, Adam and Eve's expulsion from the Garden of Eden represents the sudden, harsh transition from a pre-cataclysmic world to a post-cataclysmic one, a transition that would have seemed like a fall from grace for the survivors. However, critics argue that Thomas's theory lacks robust scientific support and relies heavily on speculative interpretations of historical and geological phenomena. However, proponents find his theory compelling due to its alignment with certain unexplained elements in Earth's past, as well as various ancient myths and legends. However, despite the controversy surrounding the Adam and Eve story, the book has undoubtedly sparked significant dialogue about Earth's history and our place within it. Whether one considers it a prophecy of doom or an intriguing exploration into our planet's dynamic past, Chan Thomas's work continues to engage viewers, challenging us to question established narratives and ponder the mysteries of Earth's cyclical catastrophes. In the end, the Adam and Eve story is a testament to the curiosity and audacity of Chan Thomas, a man who dared to present a dramatically different interpretation of our world's history and future. His legacy lies in his courage to challenge accepted norms, forcing us to critically evaluate our understanding of the Earth, its past, and its potential future. And now, Earth's magnetic poles, long considered as stable, consistent anchors of our world, are showing unsettling signs of change. The planet's magnetic field is slowly yet inexorably weakening, and the poles themselves are wandering in unpredictable patterns. And this is not a random anomaly but a part of a recurring geological phenomenon known as geomagnetic reversal, or more colloquially, a magnetic pole shift. Although magnetic pole shifts have occurred throughout Earth's long history, the exact mechanisms and implications remain shrouded in scientific mystery. However, one thing is clear: the shift carries significant consequences for life on our planet. Scientists have observed that the magnetic field strength has decreased by about 9% in the last 170 years. And what's more, the South Atlantic anomaly, an area of significantly weaker magnetic intensity, has been growing and moving westward. Both these phenomena are potential indicators of an impending pole shift, painting a picture of a future that we are just beginning to understand. However, it's important to remember that pole shifts occur over tens to hundreds of thousands of years. As of now, it's uncertain if we're on the brink of a full reversal or if this is just a temporary phenomenon. But the need to understand the implications and prepare for potential consequences is undeniable. The magnetic shift at the poles therefore represents a new complex threat. It underscores the necessity for continued research into Earth's magnetic field and its impact on our world. As we unravel the mysteries of geomagnetic reversals, we step further into uncharted territory, carrying the responsibility of safeguarding our planet and its inhabitants from the potential threats posed by this global transformation. Dr. Nicholas Thovany is a prominent figure in the field of geomagnetism, dedicated to the investigation of Earth's weakening magnetic field. His seminal work has revolutionized our understanding of magnetic pole shifts, emphasizing the critical role of the planet's inner core in these geological events. Dr. Thovany's research journey started when he observed the rapid acceleration of the North Magnetic Pole towards Russia. His curiosity piqued. He embarked on an intensive study, employing sophisticated technological tools such as satellite data and deep Earth simulation models to decipher the cryptic behavior of our planet's magnetic field. Thovany postulates that the fluctuation and weakening of the Earth's magnetic field are directly linked to the dynamics of its iron-rich inner core. The spinning convective motion of molten iron generates the Earth's magnetic field, a phenomenon known as the dynamo effect. This process is influenced by several factors, including Earth's rotation, convection currents within the core, and the planet's elliptical orbit around the Sun. Dr. Thovany's work suggests that changes in these factors could lead to the weakening and eventual reversal of the magnetic field. According to his theory, the irregular motion of molten iron within the core disrupts the magnetic field, causing it to weaken over time. And if this irregular motion persists, it could lead to a complete geomagnetic reversal, a magnetic pole shift. However, Thovany's research goes beyond just understanding the mechanisms. He also explores the potential consequences of this weakening field on our planet and its inhabitants. He argues that a weaker magnetic field will allow more solar radiation to reach the Earth's surface, which could have disastrous effects on the planet's climate, weather patterns, and the health of all life forms. Moreover, his work is instrumental in driving the global scientific community towards further research into this phenomenon. He calls for concerted international efforts to continually monitor the Earth's magnetic field and increase our understanding of the factors influencing its behavior. Dr. Nicholas Thovany's research illuminates the path ahead, enabling us to understand the causes and potential repercussions of our planet's weakening magnetic field. His work serves as a reminder that this natural phenomenon is not just a geological curiosity, but a pressing issue that could reshape life on Earth as we know it. As we grapple with this uncertain future, the scientific insights provided by researchers like Thovany will guide our way forward. And found within the many mysteries of the Earth's magnetic field, the South Atlantic Anomaly, SAA, is one of the most intriguing and perplexing mysteries. It is a region where the Earth's magnetic field is weakest, allowing cosmic and solar radiation to penetrate lower into the Earth's atmosphere than anywhere else. This region, located above the South Atlantic Ocean and stretching across parts of South America and Southern Africa, has been the subject of scientific curiosity and study since its discovery in the 1950s. The magnetic field of our planet serves a crucial purpose. It acts as a protective shield against solar and cosmic radiation, ensuring life as we know it can exist. However, in the SAA, this shield dips closer to the surface, weakening the protection and causing increased radiation levels. The exact reason for this anomaly is still under active investigation, but the leading theory ties it to the flow of molten iron within Earth's outer core. As the iron churns and moves, it generates electric currents, producing our magnetic field, but the precise structure and movement patterns can lead to irregularities like the SAA. The SAA has significant implications for space-based technology. Satellites and spacecraft passing through this region encounter higher levels of radiation, potentially causing electronic malfunctions or permanent damage. This has led to safe mode procedures being implemented by various space agencies during satellite transit of the SAA. And furthermore, the SAA serves as a natural laboratory to study the effects of radiation on the Earth's atmosphere and the potential impacts on our climate system. It provides a unique opportunity to gather data to improve our understanding of solar-terrestrial interactions. And finally, while the SAA is far from being fully understood, it underscores the dynamic nature of Earth's magnetic field. It serves as a vivid reminder of the intricate, interconnected systems that support life on our planet and the mysteries that still await to be unlocked about our Earth's magnetic personality. As we grapple with the complexities of Earth's magnetic field and the South Atlantic Anomaly, it's crucial to ponder the potential outcomes of a weakening global magnetic field. Understanding these outcomes could help us prepare for and mitigate the potential impacts. Firstly, the most drastic possible outcome, a complete reversal or flip of Earth's magnetic field, often referred to as a geomagnetic reversal, is theoretically possible. Over Earth's 4.5 billion year history, such events have occurred multiple times, though on geological timescales. The last such reversal, the Brunhes-Matuyama reversal, took place approximately 780,000 years ago. If such a reversal were to occur, it wouldn't happen overnight. The process could take thousands to tens of thousands of years. During this transition period, Earth's magnetic field could weaken significantly, even to the point of nearly disappearing before rebuilding in the opposite orientation. This could potentially allow increased levels of solar and cosmic radiation to reach the Earth's surface, affecting life and technology. While it's a potential outcome, though, it's essential to note that current evidence suggests we are not on the brink of a full reversal. Even without a full reversal, however, the weakening magnetic field could have effects on Earth's climate. While the exact connections between the magnetic field and climate are still not well understood, there is evidence of some correlation. Changes in the magnetic field could potentially impact weather patterns and ocean currents, leading to unpredictable shifts in climate. The most important takeaway is that while we can predict potential outcomes based on past data and current trends, the exact future of Earth's magnetic field remains uncertain. Continuous research and monitoring are needed to better understand these phenomena, to develop more accurate predictions, and to plan for a future in which the magnetic shield protecting our planet may look very different from how it does today. As we conclude this exploration of the fascinating and at times unsettling concept of pole shifts, it becomes apparent that understanding these phenomena is more than a matter of scientific curiosity. Our lives, societies, and technologies are deeply entwined with the stability of Earth's magnetic field, an often unseen but vital aspect of our planet. Our modern reliance on technology, particularly on satellites and advanced electronic systems, underscores the need for diligent observation and study of the magnetic field and its anomalies. Changes to this field can have far-reaching impacts on our technology and infrastructure, and understanding these changes allows us to mitigate potential negative effects. And in a broader sense, understanding pole shifts, the weakening of the magnetic field, and the mechanisms behind these phenomena can enrich our knowledge of our planet's history and its future. It can shed light on how life has evolved, adapted, and endured through major geological events, and provide us with insights into how it might continue to do so in the face of future changes. The reality of a possible pole shift, while not imminent, serves as a reminder of the dynamic nature of our planet. As we strive to meet and overcome challenges of our own making, such as climate change, it's essential that we also understand and prepare for the natural changes that Earth undergoes. Thus, the study of pole shifts transcends the realm of science, imparting critical lessons on adaptability, resilience, and the importance of harmonizing our activities with the rhythms and cycles of our home planet. As we move forward, let us do so with the wisdom gleaned from Earth's past, the knowledge of its present, and the anticipation of its future.